start the next chapter on waveguides, unless there's any questions you have about the homework or prior homework. Does anybody have any questions about it? So we're done with chapter 6. That means all the things with basic plane wave propagation, including through lossy medium and reflections, right, class? We got all that down. Now we're going to move into waveguides. How many have heard the term waveguide? All right, what a waveguide is something you guys know. What it amounts to is the ones we're going to deal with are going to be rectangular waveguides. They're simply rectangular pieces of pipe. The pipe is a perfect conductor. They're constant cross-section, and they're used to really communicate high-power microwave energy so it doesn't spread all over the place. It's just confined to that pipe. The closest analogy you have to this is a transmission line. How many know what a coax cable is? Everybody in here, I hope. What does a coax cable do? It really focuses all the electric power / energy between two conductors, right? The thing about a coax cable is that the electric and magnetic fields set up inside of them, if a wave is going this way and a coax is this way, both the E field and the H field are perpendicular to the direction of propagation. Follow me on this? Now with a waveguide, it's not so. Here's the way a waveguide, I'm going to go through the equations. Don't write this down, just listen to this. I have to give you the perspective. If I cut the pipe in half, remember it's a rectangle. I'm just going to look at it. It looks like two pieces of metal like this. Do y'all give me this? Now this height, doesn't matter what we call it. We can call it B or A. It's something. What that does is confine all the electromagnetic energy. The cross-section doesn't change. If this is the Z direction, here's what happens. Don't write it down, just listen. You're going to have a plane wave flowing this way that bangs into this surface, reflects off. Hits this surface, bangs into that one, reflects. And the reflection is going to be just about complete. It is going to be completely reflected. Nothing absorbed. Follow me? Or very little. Now there's another plane wave that's going like this. And hitting and going like this. That's how they say that if you take two plane waves where the same angle of incidence is the same angle of incidence here, and you phase them right, what do you notice? That you get propagation this way. Y'all follow me in that? Even though there's propagation in this direction for an instant, it bounces, so the net effect is propagation down that way. All right, class? Now that's what a waveguide does. It focuses all the electromagnetic energy to propagate in one direction. Got me on that? We'll be talking about a few other effects of this. So to do waveguides, and here you start writing. And you don't have to if you have your books, but you might want to make notes in your book about this because this is going to be important. If you think about this, where we started last time, we always start with Maxwell's equations. Now, I can't overemphasize the importance of understanding Maxwell's equations. It is something physicists use them, electrical engineers use them, probably a whole lot of different groups use them because they are absolutely the authority on electromagnetics. That's how all the things behave. All electromagnetic phenomena behave according to Maxwell's equations. I'm going to write down first the most general form, just like we did last time, and then the specific form and frequency domain that applies to our analysis. Generally speaking, you talk about curl of H equal to J plus the partial of D with respect to T. That's Ampere's law in the most general form of it. Now, J is real current. Follow me? That's sigma E. That means real movement of charge. This is displacement current. Follow me? This is the one we're going to be worried about. So the first thing we do is set J equal to 0. What that really is doing is saying is sigma equal to 0. Inside of a waveguide, you basically have air. Got me on this, class? And a waveguide, just so, I'm so familiar with this that sometimes I assume you are. Here's what it looks like down the pipe. It's a piece of pipe. It's got a width A and a height B. And it's constant cross-section. There are other waveguides. They're circular. We won't cover those. If I have time, I'll cover them. But we're going to do rectangular. They're the most common. How many have seen a waveguide somewhere? If you worked around any kind of microwave power, if you have a microwave in every a microwave oven, they have a piece of waveguide going in there to illuminate. It's basically guiding the power. And then they have a magnetron that creates the power. So if that's 0, the next thing that they do is say that D is epsilon E, and epsilon is the permittivity. It's epsilon relative times epsilon naught. And then what they're going to do is go and say that all the time derivatives become j omegas, because we're going to go to the phasor domain. Just like we did before. How many remember this from before? It's the, you don't really? Come on, this is exactly how we started last time, right? We started with that equation, and we made these assumptions, except for not that assumption. But we get this. So this equation becomes curl of H is equal to j omega epsilon E. That's the first one we use. The next equation is going to be Michael-Faraday's law of induction. And I'll put that over here. Michael-Faraday's law of induction is that the curl of E is equal to minus dB dt. And E is volts per meter, B is Webers per meter squared. And when we do this, we don't actually use B, we say B is equal to mu H. Now I'm going to tell you, you have to know these back and forward, because you're going to see these coming at you every which way. You got to be very, very familiar with these and the general solutions. So now when we have this equation, and using this, this becomes what? Curl of E is equal to minus j omega mu times H. You all agree with it? How many know the next thing I'm going to do? Say if I want E, only E, nothing H, what do I do? Come on. I know you know it, you're just not telling me. If I want one equation with one unknown, and that one unknown is E, what do? I did it last time several times. You're not going to tell me because you don't like it. What do? You going to tell me? Just looking at me, huh? Mm-hmm. All right. How about if I take, all right, another curl of this? I'll tell you what, let's do it with E, all right? No, wait a second. Yeah, why not? If I take a curl here, what do I get? I get curl of E is equal to minus j omega mu times curl of H, right? Remember this from last time? Now what do I do? Well, if you look at this right here, and you look at this right here, they're the same, right? So I'm going to take this, because it's just E, and put it there, and then I get curl of E is equal to minus j omega mu times curl of H, and curl of H is j omega epsilon times E. I'm doing it for a reason. I'm making sure everybody sees this. Several times. You saw it last time several times. Now you're going to see it again. You're going to get this. Now, does anybody remember what I do with this? It'll surprise me if you do, but several people know this. They're not going to say it.
Helmholtz equation again?
Yeah, I'm going to break this down using a vector identity. Am I not? What am I going to do? I'm going to say this is actually equal to the gradient of the divergence of E minus del squared of E is equal to, and then it's going to be J times J is minus 1, but there is a minus sign. So the minus sign goes away, and I have omega squared mu epsilon times E. Anybody else? There's one other thing I'm going to do, and I bet you some of you know. I got to get rid of one of these characters, don't I? I got to get rid of that one. How do I get rid of it?
Say 0.
I make an assumption. I say that what? Divergence of E is 0 or it's charge free, right? Because divergence of E is rho V over epsilon, right? How many remember that? It's really divergence of D is rho V, right? But D is equal to epsilon E, so it's divergence of E is rho V over epsilon. So we get rid of this, and this means we're assuming charge free region. All right? So that goes away, and we're left with this. The single equation is del squared of E, and then it's going to be minus, or plus, excuse me, omega squared mu epsilon E is equal to 0. That's a general form of the Helmholtz equation. This is true in free space, it's true in the waveguide. I want to do both of them right here. How many remember this, right? You remember doing this, guys? You may not remember every step. You have to remember this though, because come the first test, you'll need to know this well. Now, the next thing we do when we have this is what? That, I'm just gonna box that. Well, I'll tell you what, before I do the operations to get the solution, what I'm gonna do is just box that for now. And I'm gonna get it in H2. I wanna do them both right now. So if I wanted one equation with just H, any takers on that one?
You'd have the same equation, but it's just less u of h.
Curl of H, right? Curl of H, not curl of E, right?
Yeah.
We're gonna take another curl over here. I'm gonna do it right here if you don't mind. Can you all see me guys in the back? All right, so here I've got curl of H is equal to J omega epsilon times curl of E. I'm gonna get it. You all see that? I took the curl of H instead of the curl of E. Now when I do that, what do I replace this with? The curl of E? That's an epsilon, not a T, by the way. Well, isn't that what I do? Yeah. And so when I go here, I'm working myself into a corner quick, so I'm just gonna do this. I'm gonna go ahead and just put that as minus J omega epsilon, J omega mu, pardon me, mu H. Now I have one equation in just H, don't I? Before I have one equation in E, I'll need both of these. You follow me, class? All right, now watch. Can you all see it back there? I mean, can you see it in the forefront? Because honestly, you're looking right through his head. I'm just making sure. I absolutely hate when I can't see the board and somebody's saying, oh, you see that. All right, here, J times J is -1, but there's already a minus sign. See that? So I'm just going to get rid of it. And then I can see this is really going to be omega squared times mu epsilon H. So I'm going to do that. So now I have omega squared mu epsilon times H. And then I'm going to do one, and I'm just trying to get the same basic form of the equation I got boxed over there in H. Do you follow me? They're symmetric, it follows up. Now, I break this up using that vector identity. The curl of a vector is equal to the gradient of the divergence of H minus del squared of H, and it's equal to this, omega squared mu epsilon times H. And now, I hope you all can see this, got a comment. How can I get rid of that? Well, let me ask you this. Are there magnetic monopoles? Anybody?
Nope.
No, there's electric monopoles, that's electric charge. There are no magnetic pieces of charge that form a monopole. They're always in dipoles, at least in the macroscopic world we live in. So when I can say the divergence of B would be the magnetic charge density, there ain't no div B. I mean, there is, it's 0. Divergence of B is 0, which means divergence of H is 0. Do you follow me on this? And therefore, I'm going to get rid of this. Like that, based on what I just told you. No magnetic monopoles. You're squinting. You want me to write higher? I will.
Yeah, over.
I'm sorry about that. Let me get it over here and I'll complete this. So now I've got this, I'll put it right under here. Now I have del squared of H plus omega squared mu epsilon H equals 0. Just write both of those down for now. Those are the two equations that govern propagation in the waveguide. If you got your books, well, I'll tell you what page to turn in a second, but I want to just get your attention here. Can you all see this too, everybody? Now, here's where it gets interesting. These are two equations, and guess what? That H is a vector, isn't it? So that means when I put a sub x on here, that equation would have to be true. And when I put a sub y, that equation would have to be true. And when I put a sub z, that equation would have to be true. Got me on this, guys? It means for each vector component, that del squared operator has to be true. You follow me? In the back of your book, it has what the del squared operator is in Cartesian coordinates, and you can take a look. All right, it's a little different in spherical and cylindrical coordinates. Same thing with this. This would be true for the x component, the y component, and the z component. Now, if you think about just what I just said, in general, you have 3 vector components of E, 3 of H. Follow me? That would be what? A total of 6 separate partial differential equations that we would be solving if we want the most general form. We're not going to do that. What we're going to do is solve for specific cases that are useful to us. These are the things that actually happen in waveguides that become of interest. And what we do is define modes of operation first. So when I'm dealing with a waveguide, this write down, I'll write it nice and big here. And I want to make sure you see this. Let me just tell you, I skipped through the first part, Dr. I'll tell you where I want you to start. Start in page 388, the TM mode. But now it's a little different. You remember what TM meant before? When I said TM, it meant what? The magnetic field was perpendicular transverse to the direction of propagation, right? To the plane of propagation. Y'all remember that? Here it's a little different. All right, when I say TM mode, it still means transverse magnetic, but it's going to be transverse magnetic, no magnetic field in the direction of propagation now. So this means no H field in Z direction. So TM, when we talk about TM mode in a waveguide, there is no magnetic field in the Z direction. Do you understand that, everybody? This becomes very important. Now, when you look at this thing, the waveguide, I'm going to put it here, the cross section of it. I want you to pay attention to one thing. Remember, this wave is ricocheting back and forth, isn't it? Now think about this. If you have an electric field coming out, right? Electric field coming out. There is a magnetic field in this direction. Is there not? E cross H would be the direction of propagation. Can you all see it? If that's the direction of propagation, the wave is moving this way, and I got an E field out, and H field would be in this direction, because E cross H is the direction of propagation. Give me a show of hands if you can see that in your mind's eye. Right? Can you see it in the back? Now, do you all see how the H field has a component in the Z direction if this is the Z direction class? Can you see that? How many can see that? The H field has a Z component. I mean, yeah, right? Does the E field have a Z component? Huh? Well, if you look here for a second, the E field is out of the board, right? It's going bang, 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 right? You all see that? What about the H field? The H field's like this, right? It has a component, but there is no E field component in the Z direction for TM, right? Actually, in the book, I said start at TM. The book does the Hold it. I said something wrong. TM mode, no magnetic field in the Z direction. There's only an E field in the Z direction. Sorry. And so that means I got the wrong picture here. I'm bad. What it should be is this. The magnetic field should be out of the board. I'm bad about that. Sorry. And it should be going. So this would be the magnetic field. And if you think about that, that means the E field would be in this direction. If magnetic's out, E field has to be in the plane of the board. Do you follow me, class? So for TM, there is no magnetic field. I'm sorry, I said that backwards. So the magnetic field's out of the board, or out of the plane. This is the magnetic field, and it's doing bang, 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 bang. And that would be TM. There would be an E field in the direction of propagation. I'm sorry, I said that backwards. So what does that mean? Here's what it means and how come it's nice. If there's no H field in the direction of propagation, we can go here and say, well, there is an E field in the direction of propagation. So now I'm going to solve this. I want you to pay attention to this, and I don't want to give details that are just there to aggravate you. I'm going to try to be very clear about what you need to know and why you need to know. First thing is, you always look for the component that is in the direction of propagation when you do waveguide solutions. Since I said it's TM, there's no magnetic field in the direction of propagation. There's only electric field. Then you solve the differential equation for the component in the direction of propagation. I'm going to solve it. I'm going to have to erase that stuff. And I want you to pay attention to this part of the solution. It's important to actually appreciate this for what it is. By the way, what are we ranked now?
Number 8.
8, okay. All right. We'll see how long that lasts.
A better question, what should we be ranked?
Tennessee's fallen on hard times. All right. Now, getting back to the solution. What I have, I'm not going to complain. I'm glad I got a board to write on. When I come back to this equation, remember it's Tm. Del squared of Ez plus omega squared mu epsilon Ez equals 0. Here's how I'm going to go about the solution. First thing I'm going to do is try to minimize the constants. So when I do, y'all see this omega squared mu epsilon? The mu and the epsilon are what is inside the waveguide. Now usually it's air, but sometimes they pressurize and where they use argon, something like that, because it has a much higher dielectric strength, takes a lot larger field to break it down, so you can convey more power through the waveguide. But the mu and epsilon have to do with what's in the guide, all right, what's inside the guide. Omega squared is just a frequency. It's 2 pi f squared. What I like doing is saying, call this beta u unguided. Just say beta u unguided squared is omega squared mu epsilon. Before, beta was omega times square root of mu epsilon. Remember for a lossless case? Here, it's the u here is unguided. That's what it means in Dr. Wimmer's book. Follow me on that? U is for unguided. It means that's what it would be in free space, right? Then we have this equation. We have this del squared of Ez plus beta unguided squared Ez equals 0. You agree with me there? Now, the way I solve it is using something called separation of variables. Dr. Whitworth does this too. How many have had this in math? Do you remember separation of variables, anybody, for differential equations? Get some heads nodding. Yeah, I'm going to use this method. Pay attention to this. It's going to be slightly different than Whitworth's book, but you'll see why I'm doing it this way. So now I say I'm going to let Ez be equal to just some function just of x, I call it x of x, a function just of y, and just of z. So I've assumed this. Now if separation of variables works, then I'll be able to separate out the equation into equation just in x, just in y, and just in z. If it doesn't work, you won't be able to. That's the thing with separation of variables. You don't know if it's going to work until you try it. So I assume this, right? That's my assumption. Now I go ahead and put it in here. Now del squared of Ez really is the second derivative of Ez with respect to x squared plus the second derivative of Ez with respect to y squared. You can look in the back of the book. Plus the second derivative of Ez with respect to z squared plus beta unguided squared Ez equals 0. I just rewrote this, but I've expanded on the del squared operator. You all see that? If you look in the back of the book, you'll see this. This is for Cartesian coordinates. Then I go on and I say, well, if I take a derivative of Ez with respect to x, here's my Ez, I would take 2 derivatives of the x function, right? And I would not touch the y and z. Do you all see that? So now I get x double prime, and I'm going to drop the argument in there, times yz, plus, well, what happens when I take a 2 derivatives of this with respect to y?
X, Y, double prime, Z.
I get xz, y double prime. So I got x, y double prime, z, and finally, now I get x times y times z double prime, right? And then I got plus x, y times z here, times beta unguided squared equals 0. Do y'all agree with me here? How many see this? It's not hard to see. Just make sure you follow the steps. Got me on this? Now, My next step is important, you see it. Now I'm going to divide everything by the function x, y, and z. I'm dividing everything by this function, right? So what happens here? If I divide this by x, y, and z, the y and z go away, right? And I have x, just the function of x. When I divide this by x, y, and z, now I have y, right? Remember, I'm divided by x, y, and z, so the x and the z go away, the y is there. And this one becomes z double prime over z, right? Agreed? Finally, what happens here? Everything goes except beta u squared, right? Agreed, everyone? All right, now keep watching, stay tuned. Now here's what happens, and this should make sense. The only possible way this can be true is if this, for all values of x, is that this has got to be a constant. Because it means for any value, find a value of y and z for these things, right? If the value of this would change as I change the actual x value, that means this wouldn't be equal to 0 because beta u is a constant. Follow me? So this has to be equal to a constant. Got it, class? That's the. How many understand what I'm saying here? There's only one possible way for this equation to work. Is this has to be a constant, this has to be a constant, and this has to be a constant. Because the x, y, and z are functions of x, y, and z. Or just x is function of just x, right? So if you find the solution at 0, I move x a little. If it is a function of x, if it's a variable function, not a constant, then it will change. It won't be equal to 0. That's the idea. So we call this, right here, we call this minus beta x squared. That's what this is. It's going to be that minus beta y squared here, minus beta z squared. That's what this is. Y double prime over y becomes this, and then z double prime over z becomes that. And it's going to be plus beta unguided squared equals 0. Now that allows us to do things. Y'all remember something like this back in the days when you had your math courses in separation of varies and diffees? How many do? Anybody? 1.5 and 3/4. Yeah,
It's like a
2.
physics class. I
Huh?
think.
Physics? Is that what you guys got this in physics? Usually the math department does this. And they teach with differential equations when they solve partial differential equations. I don't know. I'm just saying that's how I got first exposure. Then you keep on seeing it over and over again. By the time you guys graduate, you're going to see this so many times you'll be sick of it. I'm already sick of it. Well, you're going to get a lot more exposure. So right here is something important happens. Now, what we're going to do is set this equal to this first. So now we come down and we say, if I have the second derivative of x, that's second derivative of x with respect to x squared, right there, over the function x, right? That's equal to minus k, or not k, beta. Minus beta x squared. Got it? Keep watching. We're just going to solve a differential equation. And remember, it's easy what really we're going to solve. So now I come out here and I get this equation. I'm going to multiply both sides by x and then bring it all over to one side. So now I get the second derivative of the function of x with respect to x squared, right there, plus, and then it's going to be beta x squared times x equals 0. I simply turn it into a homogeneous differential equation. That's the second order homogeneous differential equation. Without doing a Laplace transform or using an integrating factor, just accept this as the general form of the solution. You can see it is. In general, x, the function x, will be equal to some constant, I'll call it a, times a sine of some beta x times x, or it could be plus b times, maybe I'll use a1 or a2 times cosine of beta x times x. Now, there's another solution that it could be a e to the plus or minus j beta x times x, but that's a non-starter because that would imply propagation. There's no propagation in the x direction. So I just want you to appreciate that's the general possible form, right? And how did you always figure out the actual form of a solution for differential equations? Anyone? You applied boundary conditions. Do y'all remember that? You get the general form, boundary conditions find you the specific form, right? So when you come here, what happens? When I take these differential equations, and now I say this is my x-axis, I'm looking right down the cross-section now. I'm not looking, I didn't cut this with a z-cut, right? This is just x that way, and this is going to be y. Now z's out of the board, so the wave's propagating out of the board. You all see that, everyone? Remember, those are perfect conductors here. These are, maybe this will help. These are perfect conducting surfaces. And I'm talking about EZ, right? Now I want you to take a look. Here's the 0 point, that's 0, 0. This dimension they call A. And this dimension they call B. It's a standard. I'm going to tell you one other thing. The A dimension almost always is longer. Almost always A is greater than B. All right, that's just the way it is. I'll get to that, the reasons for that in a bit. Now, when I look at that, remember this solution here, that and that, the resulting solution, actually has, it's 1/3 of this solution. And when all these three are multiplied together, they give me EZ, right? Now pay attention to this. Well, EZ is in the direction, it's perpendicular to the board, right? I want you to think about this. What's the value of EZ at this boundary, or this boundary, this boundary, or this boundary? Anyone?
Is it 0?
Why is it 0? You're right. E tan 1 is 0 on a perfect conductor, right? Do y'all remember that? A conductor cannot allow an electric field to exist. It'll short it out. So if the E field is parallel to it, and if it, look, this is I basically took a long pipe and whack, cut it in half, and I'm looking at it. The E field is in this direction, the Z direction, right? That means it's got to be 0 everywhere, right? How many see this? Right? Y'all see it? You see it? You're looking at me like, no. I want to know if you do or not. I'm trying to make a point here. It's a very important one. You have to see how come these boundary conditions work. If the E field is coming out of this board, right, and that's easy, and this is the boundary, it's got to be 0 everywhere on that boundary. It's got to be 0 everywhere there. Everywhere there. Follow me? And I want you to think about that. Now when I look at this general form of the solution, it's got to be specifically 0 at x equals 0, right? Well, at x equals 0, the sign is 0, so that works, doesn't it? Isn't the sign of 0, 0? No matter what this is. What about over here? Cosine of 0 is 1, so the only possible value for A2 would be 0. Gets rid of the cosine solution. So that's the form of the solution, understand? Now I'm going to get rid of this constant. I'll apply the constant at the end over there to all of them. So this is the form of the solution that's acceptable, but we're not done yet. I want you to listen, and you'll see this. I know this can be a little difficult to follow. It takes you to force yourself to concentrate, but it's important. Now, the next thing you're going to see is this. When I look at this right here, it also has to be 0 where? Where it has to be 0 when x is equal to a, doesn't it, class? I mean, it doesn't have to be 0 there. How many see that? So what we do is this. We say, therefore, the sine of beta x times a, I'm using a specifically, has to be 0. All right, now my next question is, what arguments of the sine make it 0?
Some integer.
0 does? Yeah, you're ahead of me on this one. You're absolutely right. 0, right? Pi, 2 pi, 3 pi, m pi. You all agree with that? So I know that beta x times a is equal to m pi, and m is an integer. All right, now there's one value it can't have. What value of m can't it have, do you think? Well, if m is 0, what happens?
Well, you just gotta
Then that goes away completely, then you got 0, right? That means there is no m equals 0 mode here. Got that on? With me? All right, now, I mean, I'm not going to spend a lot of time on this, but it's an impossibility. That means really beta x here is equal to m pi over a. I'm using his he likes m as an integer for that one, and it's normally m for the horizontal axis. It is, it's just the standard. So that's what beta x is. In general, then we can write the solution is simply, it's going to be equal to the sine of m pi over a times x. Now we figured out even when beta is in there, what beta values, beta x values are. Got me, class? Now we move on to the next solution. Just bear with me. I'm going to do this right for you. I'm not going to do you wrong here. The next one is going to be this one, right here. And you're going to see the exact same development. Where is this in the book? You've got
This is on 389.
page 389. If you've got your books and want to turn there, you're going to see what I'm doing is in the book. I'm trying to flesh out the details, the important things. He's got a lot of extra information there, but I'm just trying to hit the high points that you need to know. So now for this one here, right here, I'm going to simply change that x to a y. And instead of beta x, it's beta y. You follow me? So I'm going to go right here, and now I'm going to say, right here, this is going to be the second derivative of y with respect to y squared over y is equal to beta y, not beta x. And that means this equation is now going to be the second derivative of the functional form of y with respect to y squared plus beta y squared times y equals 0. With me? I've virtually just changed the symbol, right? X becomes y and that's it, right? And it's from right here. Now, if that's true, that means I change this form. Now this becomes capital Y, right, is equal to really a constant, but I don't even bother with the constants here. It's going to be capital Y is equal to some possibly, I'll put it, a times the sine of beta y times y plus possibly a2 times cosine of beta y times y. Now let me get rid of this. Take a look at this for a second. Now that's the form of the y form of the variance in solution, right? How it varies with y. Well, what do I know about the E field? Remember, this y is there, and when multiplied by the two other things, it is equal to EZ. And we know EZ is 0 at the boundaries, right? I'm making that point. So when I look at this, this is the y. What is the value here when y is 0? Anywhere here. Class?
0.
It's 0, right? Now again, when I have y equals 0, this one automatically goes to 0, right? Beta, sine of 0 is 0. But this one goes to, that's 1 times a2, it means a2 is 0. That's the reason we can get rid of a2 right there. So that's the form, and I get rid of that a2, that's the form of the solution variation in y. Got it? Keep watching. Now I keep doing this. Where else is it 0? It's 0 at y equals 0 and y equals b, correct? And what does that mean?
It's gonna have some integer number of wavelengths.
Well, I'm going to do it this way. You're right. I'm going to just say sine of beta y times b is equal to 0, right? And then I look for the argument of beta y times y that makes the sine 0. And that would be what? Beta y times b equals, I'm going to use the symbol n pi because he uses n here. Are you with me? Right. Now what happens? Well, when I take a look at this, I notice that beta y is equal to n pi over b. And again, what's the one value that you don't want to see in there for the integer value? That n and m are strict integers. Class? It's 0, because what's the sine of 0? It's 0, but then the solution here, what? It collapses to 0. There's nothing. That makes no, yeah, that's the right solution, but it doesn't do us any good, because in general, we have some value of E field, but we wouldn't be talking about this. All right, so now I put this as the general form as sine n pi over b times y will be equal to my y. Leave it like that. Finally, for z, this is important. Z is in the direction of propagation. Y'all follow me on that? What happens here? We're not gonna solve for beta z in the direct route the way I did here, but I'm gonna show you something. Let me erase this. I talked to Lloyd at lunch today, Lloyd Riggs, and he teaches this course. He's been teaching it longer than me. When you're doing waveguides, you have to have somewhat of an appreciation for differential equation solutions, or they will make no sense to you. Now, Dr. Wentworth's book in his chapter does not start that way, but if you don't start that way, you won't have an appreciation for anything he says, because you've got to see where they come from. As engineers, not technicians, you start with the fundamental equations that govern the behavior, work from there to get the general forms of the solution, and then apply boundary constraints and other things to get the specific forms. It's very important we think that way as engineers. You are not technicians. Now, you can Google it, but you better know it. So here, the next one I'm going to have is this one. Now I'll just get to the point. It's going to be the second derivative of the variation in z over dz squared. And it's going to be plus beta z, all right, beta z squared, pardon me, times z equals 0, just like the other two ones, all right? Now z replaces x or y. Follow me on this, class? I got that doing this. I just equated those two, then separated, then pulled them all to one side, and I get this. Now for this one, this is in the direction of propagation. What happens is your function of z, it cannot be a sine or a cosine. It can't do that. It has to imply propagation. It could, in general, be that, but it would be what's called a standing wave. Here, we want to allow propagation in plus or minus z. And the form of the solution of this one, this is a legitimate form, becomes z is equal to some constant a1 e to the minus j beta z times z plus a2 e to the plus j beta z times z. Are you with me? Doesn't that look remotely familiar to you? What is this actually? Isn't this a wave propagating in the plus z direction? And this a wave propagating in the minus z direction? Y'all follow me now? The magnitude of A1 and A2, there would be no A2 if there was no reflected, or if there was no load. I'll get to that. But in general, we talk about propagation in the plus z direction. Now when we cap this, we're going to put a load on the waveguide, then other things change, and I'll get to those other things in a bit. Now, that means I'm basically at my final form. I'm going to have this form right here, EZ. Write this down. Make sure you write it down. Now, as a matter of fact, I'll put it up here, because on the back, that's it. This is our solution. EZ generally is going to be some constant. In the book, they call it E naught. It's literally the magnitude, maximum magnitude of E. And it's going to be times the sine of m pi over a times x times the sine of n pi over b times y times e to the minus j beta z times z. And that's the E field in the z direction. Box it. Now, this is in his book. Let me show you something. We got to get beta z, all right? I want you to watch this. Y'all see this equation right here? Hold on for a second. Let me finish this thought here. We know beta x is what? That's m pi over a squared, right? I know this is n pi over b squared, right? I don't know that, but I know this is what? Omega squared mu epsilon. So watch, when I take beta z, take it over here, I get now beta z is equal to the square root of beta x, which is equal to m pi over a squared plus, and then it's going to be, oh, sorry. I got to put beta unguided first. Beta unguided squared minus, and then it's going to be quantity m pi over a squared plus n pi over b squared. Y'all following that? So now that's how you get beta z. Still not done. This is important. With waveguides, nothing propagates in the direction of the waveguide until you go above what's called the cutoff frequency. Are you with me? It will kill everything. It's unlike a transmission line in that respect. But then when you go above what's called the cutoff frequency, everything will propagate. So what we have to do is figure out where that cutoff frequency is. And the cutoff frequency is when beta z equals 0. This is called cutoff. Well, that would be equal to, go ahead and you can square that if you want. What do I get? That's equal to beta unguided squared, right? Minus quantity m pi over a squared plus n pi over b squared. Agreed? Just let me finish this. So if I take this to the other side, now I get beta unguided squared would be equal to that. Do you all agree with me? Here we go, we're almost done. Beta unguided is omega squared times, beta unguided squared is omega squared times mu epsilon. Now we do this, we say this is equal to omega c squared, where c is cutoff times mu epsilon, is equal to this stuff. And I'm just going to put an arrow here because I'm out of time. And listen now, you can look this. You all see if I take omega c and make it 2 pi fc, then square it, take it on that side. I'll be able to cancel the pi's. Here's where it comes to, because I am about a minute over. I will get the cutoff frequency be equal to, and it's going to be equal to 1 over the 2 times square root of mu epsilon, this is in your book, times the square root of m over a squared plus n over b squared. And this is the cutoff frequency for a waveguide, where m and n are called the mode numbers. And here I'm going to stop. I'm going to pick it up on Wednesday. I'm going to give you some homework, some reading at home. I'm trying to be very clear about how this is determined. I'll give you homework. Remember, in order for this to work, you cannot have a 0, so the lowest mode possible would be for m and n to be 1. That would be the lowest cutoff frequency when m and n are 1. And then all the other cutoff frequencies are above that. All right, see you on Wednesday. I'm going to give you some homework. If you have questions about your quiz, after 2 o'clock, I'll be up at my office. Thank you.